Today we're going to look at the chain rule, and we will use this rule actually probably even more than the power rule. And that's because all the rules that we've used so far will oftentimes be used at the same time that we're going to have to use the chain rule. Okay. Now let's see what the chain rule is. So if you were to take the derivative of a composition of functions, so just meaning here we have g of x being plugged into the function f. To differentiate something like this, it looks like f prime of g of x times g prime of x. Okay. I like to call this here the derivative of the outside because we're differentiating the outside function f. And I like to call this part the derivative of the inside since it's the derivative of the inner function. Okay. Now, the proof for the chain rule is very involved, but I have posted a few Khan Academy videos on Canvas that'll walk you through the idea of the proof of the chain rule. Okay, and it's optional, but let's go ahead and see if we can apply this thing. All right, so here's our first one. We're going to try and take the derivative of 3x plus 1 all to the 7th. Okay. So is what I want you to think about for the outer function is I want you to think about f of x is equal to x to the 7th. And I want you to think about the inner function as 3x plus 1. If that's the case, then f prime of x is equal to 7x to the 6th. Okay. And so let's maybe start writing that over here. We have our f prime of x, which is 7x to the 6th. Okay. But remember, we don't want to plug in x here. We want g of x to go in here. So 3x plus 1. Actually, I'm going to scoot that over a little bit. There we go. So that part's taken care of. Now we need to take the derivative of the inside function. We need to multiply by g prime of x. Let's see what that one looks like. G prime of x should just be equal to 3. Okay. So all we're going to have here is a times 3. And so we get 21 times 3x plus 1 to the 6th. Okay. And it was really helpful to have the chain rule here because otherwise we would have had to expand this out. We would have had to have done 3x plus 1 times itself 7 times. Okay. All right, let's try another one. All right, so here again, we'll start by taking the derivative of the outer function. Okay. We're just thinking about what's in the parentheses here. We're just thinking about it as being x for a second, or t. Okay. And if you were to use the power rule, just thinking about the power rule, we'd bring down that minus 3. Okay. And we'd lower the power by 1, so to the minus 4. Okay. Now, the only thing we have left is to multiply by the derivative of the inside function. So we're going to be taking the derivative of this 2t to the 5th minus t. Okay. So that's going to be, what, 10t to the 4th minus 1. And this is our derivative here. We can simplify this a little bit, right? If you have something to a negative power, we can put it in the denominator, but then to the positive power. So if we were to combine all this together, we'd still have the minus 3 and the 10t to the 4th minus 1 in the numerator. And in the denominator, we'd have this 2t to the 5th minus t to the 4th. On to part C here, we have the derivative with respect to theta of sine of 5 theta. And before we actually write down what the derivative is here, let's actually write out what f and g are again. So the outer function here is just sine of theta, and the inner function is just 5 theta. And we know that we're going to want f prime of g of theta. So we are going to need to find f prime maybe first. So the derivative of f is cosine theta. But do remember, when I write cosine theta over here, I don't want cosine of theta, I actually want cosine of g of theta. And g of theta is this 5 theta. Okay. So there's our derivative of the outside. And then we want to multiply by the derivative of the inside. So that would be the derivative of g here. And that's 5. Okay. So it's just this times 5. Okay. All right, let's look at part D. This one's a little bit more challenging, but there is a trick to this. Whenever you see these trig ones that are raised to a power, well, the notation that we use for raising trig functions to powers sometimes makes you forget exactly what it means. Okay, and let me actually write what I mean here, which is that this cosine cubed of theta, I could actually just rewrite this as cosine of theta cubed. And now this actually looks like maybe something I can do with the chain rule. I can see what the inner function is and what the outer function is. Right, so our outer one this time would be theta cubed, and the inner function, which I'll write as g here, is that cosine of theta. And so if you were to take the derivative of the outside function, right, you'd get 3 theta squared. But I'm not going to use theta. I have cosine here, so cosine of theta squared. Okay. So it essentially looks like we've just applied the power rule. And now we want to multiply by the derivative of that inside function. And so the derivative of cosine of theta is minus sine of theta. And there's not a whole lot more we can do with this. Okay. This negative, I'll bring it out front, and that's really about all I'll do. All right, on to D. This would be a good one for you to pause the video and give this a try. Now that you've given part E a try, let's see what we end up with here. I'm actually going to rewrite tangent to the 10th of x squared before I move on to the next, or before I start differentiating. So we have tangent of x squared, and then this function is being raised to the 10th power. Again, writing it this way is just helping us see the composition of functions here. And we actually have, we're going to have to use the chain rule technically twice here. And we'll see why here in a minute. So if you start taking the derivative of the outside, I think you all know it's going to look like the power rule. Bring down the 10. We have our tangent of x squared in here, and then to the 9. But now we want to take the derivative of the inside function, this tangent of x squared. Well, the derivative of tangent is secant squared, so we have secant squared, but this is of x squared, right? So there's actually another inside function. So if you were to take the derivative of this innermost function, x squared, its derivative is going to be 2x. And this is another one where we can't do a ton of simplification. So all I'm going to do here is multiply this 2x and the 10 and get 20x. And I'll rewrite this tangent of x squared to the 9th in our typical notation, which is tangent to the 9th of x squared. And then we still have the rest of the secant squared of x squared. All right, in part F here, this is another one I think you should pause the video and try. All right, so part F here is going to require a combination of the quotient rule and the chain rule. So if we're using the quotient rule, we're first going to take the derivative of the top, which is just 1, times the bottom function, and that's actually cosecant, not cosine. So cosecant of 3t, minus the top function, which is t, and then times the derivative of the bottom function here. And if you're going to differentiate this function down here, it will require the chain rule. So let's just think about the derivative of cosecant for a second, as if there was not a 3t there. Well, the derivative of cosecant of t is going to be minus cosecant cotangent. But we have those 3 t's in there, so this is going to be cosecant. And actually, I don't want to forget my negative sign here either. Minus cosecant of 3t cotangent of 3t. And then I still have to take the derivative of the inside function, 3t there. If you take the derivative of that, that's just 3. And then this should all be over that cosecant of 3t squared. So cosecant squared of 3t. All right, and let's go ahead and distribute, see if there's anything we can maybe combine here. Doesn't look like there's going to be, but so we have cosecant of 3t. We have a double negative, so plus 3t times cosecant of 3t cotangent of 3t, and then all over that cosecant squared of 3t. All right, and you might notice that there's actually some cancellation we can do here because there's a common factor between the numerator and denominator. But before I try and cancel, it might be a good idea to actually factor so I can see precisely what's going to cancel. So if I factor a cosecant of 3t from the first term, that just leaves me with a 1. And then if I factor out a cosecant of 3t from the second term, that's going to leave us with a 3t cotangent of 3t all over cosecant squared of 3t. And I think I have just enough room here to write our final answer. We can now cancel a common factor between the numerator and denominator. So that would be a single cosecant of 3t from both the numerator and denominator. So we're left with 1 plus 3t cotangent of 3t all over cosecant squared of 3t.